Thanks, Bertel and John and Fedor. I don't see you. Okay. Thank you for putting us on the program. Thank you for organizing everything. This is joint work with Jaap and our former student, Nan Yang, who is now spending most of his time at Amazon Japan. This is a follow-on paper to an earlier paper the three of us had with Jan Tilly on the characterization of Markov-Perfect equilibria in a dynamic oligopoly model with sunk costs and stochastic aggregate profitability shocks. What we add in this paper to that previous work is stochastic firm-specific technological progress. The other things on this list of things in our game, sunk cost of entry, stochastic aggregate profitability, and opportunity cost of production, so there's a reason to exit, they were all present in our previous work. We're adding the technological progress here. It turns out that was pretty difficult. So that's why this is one paper by itself. What are our key assumptions in this? At most, two firms produce at once. So this is a duopoly model. And that's an assumption that we need. I'll explain why later. But we could not get the results we have if we allow three firms or more. Firms, technology types, there should be a possessive there, I apologize, only increase. Firms make exit decisions simultaneously, and they potentially use mixed strategies. So in much of the dynamic oligopoly literature, firms have privately observed conditionally independent cost shocks that would purify an otherwise mixed strategy. We need mixing here to get existence of a symmetric equilibrium, okay? And then there's a restriction that we use. We find it very natural. We saw this in a paper by Luis Cabral, and for years we went around saying that Luis called this natural equilibrium. And then I had lunch with him one morning, or breakfast with him one morning. He said, I really thank you for studying my paper. I like the name, but I don't think I used that language. And he was right. And so we named it natural equilibrium. So high technology firms never exit while leaving a low technology rival behind. Okay, so having the high technology gives you, in a sense, a strategic advantage, okay? What do we get out of this? We get an algorithm. I'll go right there. What we get out of this is proofs of equilibrium existence. That's relatively easy, and uniqueness. That's the much more substantial thing. And the equilibrium uniqueness proof is wound up with with the demonstration of an algorithm that calculates the equilibrium quickly using contraction mappings. Okay, so for example, Ariel's pioneering work on this, there was a mapping that related current payoffs to future payoffs and the play of a game. And that mapping satisfies one of two of Blackwell's sufficient conditions for a contraction, but not the other. In particular, it's not monotone. It's possible to increase everyone's continuation payoffs, and yet through the play of the game, make everybody worse off. Okay, if you change their slopes in the right way. We're actually going to be working with contraction mappings themselves. The mappings we'll work with are guaranteed, once we do standard Bellman equation iteration, they're guaranteed to converge in the usual way that we're familiar with, okay? What's the enabling insight here? It's essentially the same insight that we had in our earlier paper, but everyone ignored that, so we decided to speak more loudly. And we're going to call that fake backwards induction, FBI, in honor of our most recently retired president. So this game has no terminal nodes, so you can't do backwards induction directly. And it's not a directed game like our three hosts have worked on, okay? Nevertheless, we can use insights from backward induction in this game, because we know that when firms, there's two firms here, their firm's expected payoff must equal 0 whenever they both choose a positive probability of exit. That pins down the continuation value of both players in some nodes of the game. Which nodes exactly is not clear ex ante, that's going to come out in the computation, but in some nodes. And we can start to unravel the payoff structure from knowing that. So those nodes, we'll call them fake terminal nodes. Okay, I'm not going to use that terminology again. Okay. Once we unravel the payoff structure, turns out the payoffs are going to satisfy a set of, going to be the solutions to a set of dynamic programming problems. They're going to be the value functions associated with those. Those dynamic programming problems are going to be misspecified in a deep way. Okay. But the values that come out of them are going to be the correct equilibrium values for the game. That's what makes this, that's the insight that makes this work. Once we have those values, we can determine the strategies that make that firms play in that equilibrium. Okay. And I hope you can start to see why we're going to get uniqueness here. We're going to be playing with Bellman equations. And at some point, we're going to demonstrate that these Bellman equations are necessary for any equilibrium. Since the Bellman equations have unique fixed points, that means we're working with the only equilibrium. Okay, so that's the logical structure of what we're going to do here. Why bother? We should always ask that. So I think we bother because oligopolies create and implement technological change. We just saw that. Thank you, Ashley. And thank you for identifying me as the king of empirical imprecision at this conference. So I'll stick to theory for this paper, for this talk. So that's ultimately why we care. We're working towards, I think, the same thing that Ariel pointed us towards 25 years ago, which is that oligopolies create and implement technological change. And if we don't, we're never going to understand that process of the world becoming more productive until we understand the oligopolistic interactions in that. That's, I think, our opinion. But there are trade-offs relative to previous approaches to this. Well, obviously not the first ones to be thinking about this. The trade-off relative to Ariel's work and the Doroshelsky-Satterthwaite follow-on is that in our world, the cost is that in our world, technological progress depends only on continuation, not an investment. So these firms, the only investment they're making in technological progress is their existence. And they do invest in that. And aggregate technological progress can go faster if there are more firms. Okay, but that's the only way it can go faster. All right. The benefit is that we have equilibrium uniqueness and super fast computation. So I'll give you an example at the end, but it takes 30 seconds to compute it on my laptop. Okay. We have this earlier work. The cost here is that we're limited to duopolies in this paper. In that paper, we had general oligopoly. But the benefit here is that we're going to have persistent post-entry heterogeneity. So another way of looking at this paper is that we're combining our earlier work with something like Hugo Hoppenheim's model, where firms evolve stochastically after entry. Okay. But we also think there's a complementarity with that earlier work, specifically work with a richer model, but a model with a less well understood equilibrium set, is that we can use anyone, not just us, you can use our model as a starting point for a homotopy method. Okay, that might speed up computation in those other models too. We have a master's student, Carlo De Vos, who did exactly that in his master's thesis. So we've seen it work. Okay. So The model itself, all the primitives are on this page. Okay, we're going to work in discrete time and with each period subdivided into game stages. Firms are going to discount payoffs over between time periods with beta. At any given moment, either 0, 1, or 2 firms can serve the market, no more than 2. Firms' technology types live in this set 1, 2 through K check. So there's a bound to how good a firm can be. K check is the best. Okay, that's why it points down. It's the best. K check could be really, really big in practice, so that for a given application, you might practically never run out of improvements, but we do require it to be a number, not infinity, okay? The payoffs from production depend on your type, the type of arrival, if you have one, that's X, and an aggregate exogenous state Y. So X can be 0, which means that there's no rival, or it could be one of your states as well, okay? The exogenous state follows a Markov process. After production, potential entrants sequentially, so there's either 0, 1, or 2 potential entrants. That kind of depends on whether there's firms in the market, how many firms there are in the market. We could get more complicated about that, but this is the simplest thing to do. So if there are 2 potential entrants, the market's empty, and they make their decisions sequentially. If there's 1 firm in the market, there's 1 potential entrant that makes its decision all by itself, okay? To get into the market, you have to pay a sunk cost. The sunk cost potentially, but need not, depend on the type of an incumbent rival. And it does depend on the exogenous state. Within this exogenous state, we go into detail in the text. Within this exogenous state is a conditionally independent error term that affects all potential entrants' costs and acts as the econometric error. We don't do any econometrics in the paper, but having absolute continuity of that error actually helps us with some technical stuff in the game. So we put it in, okay? After entry, this sounds weird, but it works. After entry, all incumbents and new entrants simultaneously make continuation decisions. Now, obviously, nobody is going to pay a sunk cost in order to immediately exit. Okay, so that's not going to happen on the equilibrium path. But this was a convenient way of setting up the timing. So they make simultaneous exit decision or continuation decisions. If a firm chooses exit, it receives the continuation payoff 0 and it's never heard from again. If it chooses to continue, it has to pay the continuation cost kappa of Y. The something I should have mentioned here, but did not, potential entrants only get 1 shot at entry. So there's no ability to hoard an option to enter later, okay? Every entrant either does it now or forever hold your peace, okay? After this sequence of events, the aggregate state evolves and any active firms draw new values of their technological types from independent Markov processes. And these have a transition matrix, we call it pi. So that's all of the model primitives. Okay. There are a few technical assumptions. Let me talk about the economically relevant assumptions though. So first of all, this is going to be a model where in flow payoffs, my presence and John's presence were competing against each other for strategic substitutes. I'm less happy when you're there, you're less happy when I'm there, okay? Not only that, but the stronger is John, the less happy I am, and vice versa. And the stronger I am, the happier I am. Okay, so this first assumption here says, better types make me better off, increase my profits. John improving his type makes my profits go down. The last thing there is a little technical thing for boundedness, which is familiar from any dynamic programming application. Okay. The next one, again, is about keeping us as substitutes, not complements. The only thing that can happen to the cost of entry is by suppose John is the incumbent and his type improves, the cost of entry can only go up, not down. Okay, so I'm not learning from him, for example. All right, that's why we call this a barriers to entry assumption. So there's this older AER-PMP by McAfee, Malon, and Williams that defines a barrier to entry as exactly the difference between this and this. Okay, it's a part of the sunk cost that a subsequent entrant had to pay that an original entrant did not. So we allow for that, but it's not necessary for anything that we have. We just make sure that we just, make it clear that the model can handle that. The next two assumptions are on the technology dynamics. The first is that if I have a higher type, then the distribution over technology tomorrow stochastically dominates the distribution of someone with a lower type. Okay, that's a fairly clear thing. That's keeping the static incentives to have a higher type and the dynamic incentives aligned. That's the way we think of it. And then this is a big one that really drives everything we do. Okay, pi is upper diagonal. That means you can only get better. You can't get worse. Okay, you could be overtaken. Your profits could go down. Your profits could go down either because a rival that was initially low type overtakes you, or because there's a bad aggregate shock. But you don't forget how to do things. Okay, you're constantly striving to do better and you're not forgetting that. Okay. Yes. I will. Okay, so the reason it's not a directional game is because the game as a whole can revert to lower types. Okay, depending on the realization of the Y, a bad realization of the Y could potentially clear out both John and I when we're both good types. And then a good realization of the Y could later put you and Bruno in as competitors. So it's not directional in that sense. Aria? Yes. Yes. Exactly. Yes, it does. Exactly. It's exactly that. That's exactly it. Yes, that's exactly it. So it's not technically a directional game. It has a lot of features of directional game, no question about it. Okay, and we learned a lot from you guys. But there is no place where we can say, okay, once the game is here, it never leaves. Let's solve the DPs for that, given that we're both continuing, and then unwind. It's very similar, but it's not exactly that.
Could you use this trick of Gettler and Gordon of thinking about a path of infinitely increasing technology, and that K is relative to the state of the art that's constantly improving?
That's something I would like to try working on, but we haven't gotten there yet. I think there's also, you had an outside option that was continually improving. And that's something that we would want to build into this, but we have not gotten there yet. Okay. Yes. This might or might not be stationary, depending on how often the market gets cleared out because of a demand collapse. Right. Okay. There's a lot of math on this. But it's all pretty simple. We're going to look for Markov strategies. There are two decisions to be made. If you're a potential entrant, do I enter or not? And if I'm an incumbent, do I survive or not? Potential entrants always move alone, so we let their strategies be pure. Their actions are pure. They're always going to take a pure action. Okay, so their strategy is going to map the type of any incumbent and the value of the demand state into 0, 1. The survival rule is going to map those decisions are made simultaneously. That's where the mixing comes in, potentially. So that's going to map your own type, your rival's type, if any, and the demand state into the interval 0, 1. Okay. In a symmetric Markov-Perfect equilibrium, all players follow the same Markov strategy. Okay. We're going to keep track of the expected discounted payoffs at 2 of the nodes within a period and give them special attention. We call them VE and VS. VE is the post-entry value. So it's immediately after the entry stage. What is the value of having type K given and your rival having type X and the demand state is Y? Okay. And then VS is immediately following the survival game. Okay, we played our strategies, maybe they were mixed. I happen to survive. I have type K. My rival has type X. What's my value of being in the game at that point? And these obviously interconnect. Okay, so what we have, I'm not sure how much detail I should go into this here. If I just entered, if I choose to survive, so this is the probability of survival. I'm a monopolist, excuse me. Suppose I'm a monopolist. I choose this is my probability of survival. This is what I get if I survive. Okay. If I face a rival, I choose survival, and then my payoff depends on what my rival does. Okay, this is the probability my rival survives, and we both get the post-survival payoff. Probability my rival leaves, I get the monopoly post-survival payoff, and I have to pay the cost of continuation. Okay. Then the post-survival value is discounting payoffs into the future and accounting for the entry decisions of a potential entrant, if any. All right. We're going to look, as I mentioned in the introduction, for a natural Markov-Perfect equilibrium. That's our word. We don't mean it to be too propagandistic. It is what it is. Okay. It says that if I have 2 types, L and H, we're looking for an equilibrium where if a type L producer facing better type H chooses survival with a positive probability, then the better type H survives for sure. That's the restriction we're going to put on strategy. Excuse me, let me be very clear. We are going to look for an equilibrium in that with that property. We are not constraining the strategy space to have that. Of course, we're going to look for you could deviate in all kinds of ways. Okay, but we're going to look for an equilibrium with that property. Okay. Now, with that, that's the model. The stage is set. Okay, those are the players. What I want to do for most of the rest of the talk, how much time do I have, Mark?
We now have 23 minutes.
Okay. For most of the rest of the talk, what I want to do is walk through the computation in the case where there are exactly 2 types. That's already a little bit complicated, but it illustrates the moving parts without any more complication. All right. So the way we do this is we think about the state space for the model as being partitioned into 5 sets. Each of these 5 sets is illustrated by these boxes, one on top of the other. The top number in a box tells you the number of type 1 firms in the market. The bottom number tells you the number of type 2 firms in the market. So there can either be 2 type 2 firms, 1 type 2, 1 of type 1, 1 of type 2, 1 type 2, 2 of type 1, or 1 of type 1. Okay, these are all the possible configurations for the number of types, for the number of firms in the market. Okay. And what we're going to do is we're going to start this unwinding of the profit of the continuation values. And we're going to do it here. We're going to think about markets where, or initial states where there are 2 type 2 firms and obviously then no rivals. Let's think a little bit about what those profits look like. Okay. Now, when they get to their survival, there is no entry, okay, because the market's full. When they get to their survival sub game, okay, they play this reduced form. This reduced form says if we both survive, we each get the duopoly continuation value minus the cost of continuation. If one of us chooses survive and the other exit, then we get the appropriate monopoly or zero payoffs. And if we both choose exit, we get nothing. For the moment, and only for the moment, presume that the payoff to being a monopolist as type 2 exceeds the payoff to being a duopolist. That makes sense intuitively, but it's something you got to prove. Okay. It makes sense intuitively because it's something that's true for the flow payoffs. But I mentioned earlier that I can't extend this to 3 or more firms. It's exactly at this point where things fail. It's actually possible for me to benefit from another rival if there's even though my flow payoffs are lower, and I benefit from that rival because she's deterring further entry. Okay, so suppose that we have that, then the equilibrium is actually this game has a unique symmetric equilibrium outcome. If this number is positive, we both pay survive. Okay, if this number is negative and this number is positive, the monopoly payoff, then we would both like to be the sole survivor, but we can't both be the sole survivor. The only symmetric equilibrium is mixing. The payoff to mixing is 0 because exit is in the support of the mix of the strategy. And if this number is also negative, then we both choose exit with probability 1. So the payoff to this game is the maximum of this and 0, the duopoly payoff and 0. That's excellent. So if you write it out this way, combining what the post-entry and post-survival payoffs are, that says that the post-survival payoff today is beta times the maximum plus the continuation value, that whatever profits I get, plus the maximum of 0 and whatever is realized tomorrow. I don't know. This is the sense in which is different than a directional game. This 0 encompasses 2 things. It encompasses we both want to leave for sure, and we're going to mix in equilibrium. Okay, that mixing lets the game go to a different set of states. Okay, so that's the sense in which it's not a directional game. It's that mixing allows that to happen. Okay, and you look at this baby and you say, this is a contraction mapping. And you get I got real excited. I got too excited, in fact. And then Nan kind of calmed me down. And because I didn't realize, like, I had to assume that, I mean, I was just, yeah. He got me my meds, I was good. But still, this is a contraction mapping. So there's a unique continuation payoff that satisfies it. Yes. Okay. Yes. Both the guys could go out as a random error, and both of the guys could come in as a random error, but in expectation, it's 0. That's exactly the insight. Is that yes, those are both possible. All of that's possible in mixing. Okay. But knowing that I'm going into mixing, my payoff ex ante taking the expectation across the other guy's mixed strategy, has to be 0, no matter what I do. So yes, I could go to all these different places. That's exactly right. That's exactly right. But ex ante, I know that I'm going to be 0. Okay. Okay. Thank you for pushing pause. Okay. So we've got that. Let me go back to this little figure now. The computer was my first computer. It's an Atari 400. I bought it in 1978. My father gave me $300 and I used $300. And it was the best. My father said that was the best $300 he ever spent. So the computer, we've got this now. I put a number in red if we're calculating the continuation value for firms with that productivity type. So that's what we were doing now. Now we have that in hand. What's the next step? The next step for us is to calculate the value of a firm that is low type or type 1 facing a type 2 rival. That firm has a there's a chance it could progress and become type 2, but we know its payoff then, right? Its payoff is what we just calculated in that state. It could stay the same. Okay, that's the payoff we're calculating. It's not going to become a type 1 monopolist because it never outlives a better type rival. That's the restriction of a natural equilibrium. And so its dynamic programming problem is completely specified. And we can calculate it again. It's just a dynamic programming problem at that point. We can solve it. Okay, that will give us 2 things. It'll give us, well, 3 things. It'll give us the value of being that type. It'll give us, once you have the value of being that type, you can see when it's worthwhile to give up being that type. So we get the rule for continuation for someone in this situation. And we get the rule for entry to being someone in that situation. Okay, yeah, John.
So you make that assumption. Could you drop that assumption and calculate it maybe in a more numerically intensive way, like by backward induction?
Which assumption?
The assumption
There's so many.
Equilibrium that the behind firm can never leapfrog and become the leader.
No, the behind firm, okay, in only 2 types, they can't become the leader. With 3 types, they can leapfrog. But what we're saying is not that they can't leapfrog. They can. Thank you. It's a great question. They can leapfrog. What we're saying is at that moment, your better type rival won't choose to exit when you choose to continue. But yes, if you're behind, you can still leapfrog.
Arrive in equilibrium instead of assuming. In other words, you're using that in some way.
I'm using it a lot.
Relax it, not assume it, calculate the equilibrium, and then say, oh, hey, it actually is, I don't have to make that assumption.
So
it's going to be a property of the equilibrium.
I have a 2-part answer to that. Number 1 is I can't do that now. I have no idea. Number 2, when smart people have asked me questions where I say, I don't know, I can't do it, like 3 days later, I figured out how to do it. So thank you for pushing me, and hopefully that'll happen again. I'm going to demonstrate that. Yes, that I'm going to demonstrate. Okay.
So should I think of the natural equilibrium and the symmetry assumption as like an equilibrium selection? Or?
Yes, think about the natural equilibrium and symmetry as like equilibrium selection. Absolutely. Absolutely. That's right.
So that's what gives you the uniqueness you can do that.
It's unique within that class. Okay. It's unique within that class. Okay. So, okay. So once we've got that guy, the next step to do is to think about the problem of a type 2 firm facing either one type 1 rival or no type 1 rival. Those two values have to be solved together because type 1 rivals can come and go. 10 minutes, thank you. Type 1 rivals can come and go. So those two things have to be solved together. All right, and so but again, that firm can transition to being a type 2 duopolist with facing an equal rival, or between these two states. And that firm then, so we're able to write down a Bellman equation that the value function has to satisfy. Once we solve that Bellman equation, we get one more thing out of this. Well, let me just leave it. We get the value. Let's just say all we get actually is the values of being a type 2 firm, either alone or facing a type 1 rival. The fourth step, oh, I've got a bunch of math here, but I don't like it. I mean, it's correct. It's just, I think this is easier. The fourth step is to consider the market when we begin with 2 type 1 firms. So both firms could potentially do better. Now, from the stochastic evolution of their types, they could either stay where they are or jump to any one of these. They could both jump to type 2 together. One of them could jump while the other one doesn't. Actually, I shouldn't have said this. They can go to here or here. Okay. If they choose exit, again, if they choose exit with a positive probability, again, their payoff is 0 in expectation. Although we don't know the individual terms and calculating that expectation, we know the expectation. And so we can use the same fake backward induction trick there to calculate the payoff of 2 type 1 rivals. Once we have that, we can calculate the value of being a type 1 monopolist. That type 1 monopolist could attract an entrant or could attract a rival, in which case it goes here. It could not attract a rival and get technological progress, in which case it goes here. It could attract a rival and technologically progress, in which case it goes here. Okay, but I have all those payoffs. I have the payoffs to all of those things. So the only decision this type 1 monopolist is making is whether to continue or not. That's a straightforward dynamic programming problem. So we solve it. Okay. Now, at this point, we're basically done, but what we don't have in particular are the mixed strategies. We said you're mixing at these points, but we don't know what the mixed strategies are. But now that we know the payoffs, we can calculate them. And that's what we do in the last step. Okay. So that's the way in which we can calculate this equilibrium relatively quickly. All right, now that I've got in the slides, which I guess are on the archive now for the conference, there's a little bit of explanatory math behind all of this for each one of these steps. Okay. Yeah, I didn't want to put myself to sleep by reading it. Okay, let me see. Yep, I said all that. Great. Now, what do we have to prove? Okay, so that's an algorithm that computes something. What do we have to prove? I think you, Ariel, asked if there is such an equilibrium. Well, we're going to demonstrate that yes, there is by showing that this is 1. What we just calculated is 1. Okay. But we have to show that it's an equilibrium by verifying that the calculated survival rule indeed satisfies that natural restriction. Okay, and we do that. We do that by showing that the continuation value inherits the monotonicity properties of the flow payoff value. All right, that is, it weakly increases with your own type, weakly decreases with your rival's type. Okay, then to establish that this is the only equilibrium, we show that this post-survival value must satisfy those monotonicity properties. since it must satisfy those monotonicity properties, that turns the Bellman equations that I created by assuming that monotonicity into necessary conditions for the equilibrium. Okay. So, now that was just the type 2 case. What do we do in general? In general, we allow for K check bigger than 2. We have a nice little flow chart. If you're having trouble sleeping, you can look at our flow chart, and that will help you. We established that the extended equilibrium indeed calculates a natural MPE, and we established that the natural MPE is unique. Okay, through that same basic procedure, that the monotonicity conditions that that we impose on the continuation value indeed are true for any equilibrium continuation value. Okay. And then computation time. So that's I'm a big fan of vintage technology. That's a Cray supercomputer from the 70s. Jaap commented it looked like the aquarium that just burst in Berlin. You could have your beverage of choice on the side and sit there, while in fact Seymour Cray wanted you to do that. But we don't need a supercomputer, okay? So I did this on my laptop. I set K-check to 30. YT contains 2 components, the persistent demand state, follows a Markov chain with 201 points, and then the conditionally independent shock to smooth things out on the continuation and entry margin. There are 186,930 possible combinations of the demand state with the 2 firms' productivity values. That's the number of continuation values we need to calculate. Okay. If we set beta equal to 0.995, the average computation across 100 computations while my browser was open, I mean, nothing special, was 37.6 seconds. So this goes fast. All right. If you set beta to be even lower number, not surprisingly, it goes even faster. Okay, because that's what contraction mappings do. So, like I said earlier, I hope that this peek into one little part of the equilibrium set of this model, which itself is a special case of a model that I think we all know and love, proves useful. If you choose to use it as a homotopy, that's great. I hope it proves useful just as a baseline. Say, okay, I know this about the properties. So if I find multiple equilibria, then they must not satisfy one of these restrictions. That might be just fine for your application. Okay, but at least you understand that then. So I'm done. I have one little pitch. I'm sorry. I have one little pitch. I'm almost done. So I found, this is cool. I found this in my dad's papers. He passed away a few years ago. It is graph paper with a logarithmic probability scale on the vertical axis and a log scale on the horizontal axis. My dad worked in quality control at Ford. And so this is printed by the Ford Motor Company in 1970. And it says that it's Weibull probability paper. And so if anyone wants a piece of vintage technology, I'm just going to put it up here. I think it's cool. It's this translucent stuff. I think it's really neat. So I brought it. This is probably the only group of people I can imagine who would appreciate it. So I brought it to please take one. Okay.